For millennia, humanity has gazed at the sky with the same quiet unease, not to count stars, but to understand its own origin. How did everything begin? Was there an initial moment? Or has the universe always been in process? Modern cosmology offers no simple answers. Instead, it reveals a deeper scenario, where time may have no clear beginning, nothingness may be full of activity, and the Big Bang ceases to be an endpoint and becomes a boundary of knowledge. This account does not seek absolute certainties, but rather explores how science approaches the greatest mystery of all, the origin of reality itself. For centuries, humanity looked to the sky with an apparently simple question: what existed before everything? The formulation seemed natural. If everything has an origin, the universe must have one as well. Yet that question concealed a trap. It assumed that time existed before time itself, that there was a prior stage in which something could begin. For a long time, no one noticed the problem. Language seemed sufficient to sustain the doubt. At the beginning of the 20th century, most scientists shared a comfortable idea. The universe was eternal. It had not been born, nor would it die. It simply existed. Stars moved, galaxies rotated, but the whole remained unchanged. This view fit well with human intuition. A stable cosmos offered intellectual security. It did not demand answers to uncomfortable questions about the ultimate origin of reality. That calm did not last long. In 1929, the study of light coming from distant galaxies revealed something unexpected. When their spectra were analyzed, the light appeared shifted toward longer wavelengths. This phenomenon, known as redshift, indicated that those galaxies were moving away. But what was truly unsettling was not only that they were receding, but that the farther a galaxy was, the greater its apparent speed of separation. The implication was impossible to ignore. The universe was not static. It was expanding. This expansion did not mean that galaxies were traveling through a pre-existing empty space like projectiles. It meant something far more profound. Space itself was stretching. Distances were increasing because the very structure of the universe was changing over time. Suddenly, the idea of an eternal cosmos began to collapse. If the universe is expanding today, then in the past it must have been smaller. And if we go far enough back in time, we arrive at a state in which all matter, all energy, and all space were concentrated in an extreme form. This was not a point floating in nothingness, but a limiting condition in which our physical laws ceased to function normally. That initial state came to be called the Big Bang. The name, popular and misleading, generated more confusion than clarity. It was not an explosion in a specific place. There was no center and no edge from which matter spread outward. The Big Bang was the expansion of space itself. With it, space and time were born. There was no outside and no before, in the everyday sense of those words. This idea is difficult to accept because it contradicts how we usually think about reality. Our daily experience trains us to imagine causes preceding effects, moments following other moments. But when speaking about the origin of the universe, those categories are no longer reliable. Time is not a pre-existing stage on which something happens. It is part of what happens. In the earliest moments after the expansion began, the universe was an extreme environment. The temperature was so high that no stable form of matter could exist. There were no atoms, no nuclei, no composite particles, only a chaotic ocean of elementary entities interacting constantly. As time passed, as the universe expanded and cooled, increasingly complex structures began to form. First came protons and neutrons. Later, these combined into nuclei. Hundreds of thousands of years afterward, electrons were able to bind to those nuclei and form the first atoms. Matter ceased to be an opaque soup, and the universe became transparent to light. Millions of years later, gravity gathered enormous clouds of gas that collapsed until they ignited the first stars. Complexity did not arise from a prior design, but from a gradual process governed by simple laws acting over vast periods of time. Accepting the Big Bang, however, did not resolve all doubts. In fact, it opened new and even deeper questions. If space and time began there, does it make sense to ask what happened before? Is it possible for something to arise from nothing? Or is the word nothing misdefined from the outset? Some physicists argue that the Big Bang marks the beginning of time itself, and that, therefore, there is no before. In this framework, asking what existed before the universe would be like asking what lies north of the North Pole. The question loses meaning, not because it is forbidden, but because it relies on concepts that no longer apply. Other scientists are not satisfied with that answer. They argue that even if classical time has a beginning, there could exist a deeper reality in which other forms of time or prior processes play a role. This tension between what we can describe and what we can imagine lies at the heart of modern cosmology. What became clear from that initial discovery is that the universe has a history. It is not a fixed stage, but an evolving process. And understanding that process requires abandoning old certainties and accepting that even our most basic questions may be poorly framed. The Big Bang did not only change our understanding of the cosmos, it changed our relationship with reality. It forced us to recognize that the universe is not given once and for all, but has a past, a development, and perhaps a future we do not yet understand. With that shift, the original question ceased to be simply, what was there before? And transformed into something far more unsettling. What does it really mean to begin? Accepting that the universe had a beginning resolved an ancient question, but opened another, even more troubling one. As scientists observed the cosmos with increasingly precise instruments, they discovered that the universe not only changes over time, but does so following a surprisingly regular pattern. On large scales, reality appears organized with a coherence that is difficult to reconcile with an extreme origin. The problem became evident when studying the cosmic microwave background radiation, a faint signal that fills all of space and comes from an early stage, when the universe was only a few 100,000 years old. This radiation preserves the thermal imprint of a young, hot cosmos. If the birth of the universe had been turbulent, it would have been reasonable to expect large differences between regions. Yet the data showed the opposite. The radiation displayed remarkable uniformity in all directions of the sky, with only minimal variations. Regions of the universe that today are separated by immense distances shared almost the same temperature and physical properties. It was as if they had once been connected, even though, according to classical physics, there should not have been enough time for that to happen. This finding raised a fundamental question. If nothing can propagate faster than light, how could the universe have achieved such a degree of coherence from its earliest moments? The traditional Big Bang explanation was insufficient to resolve this dilemma. To address this problem, a radical idea was proposed in the early 1980 seconds. Instead of a uniform expansion from the beginning, the universe would have undergone an extremely brief phase of accelerated expansion. This was not ordinary growth, but a violent inflation of space itself. In a tiny interval, the size of the universe would have increased dramatically. During that phase, regions that were originally very close together became separated by colossal distances. Before inflation, the entire observable universe would have fit into a very small volume, allowing its different parts to share information and reach a common state. Inflation would have locked in that initial uniformity and spread it across the entire cosmos. This process also explains why initial irregularities did not dominate the structure of the universe. By stretching space so rapidly, differences were smoothed out, like a wrinkled surface that becomes flat when pulled tight. The result was a homogeneous and coherent universe. Inflation did not only solve a conceptual problem, it also made observable predictions. The small variations detected in the cosmic microwave background would be the result of microscopic fluctuations amplified during that early phase. Over time, those differences would give rise to the large-scale cosmic structures we observe today. Many later observations fit well with this scenario. Even so, inflation did not answer every question. It describes how the universe could have become organized, but it does not explain what triggered inflation or why it occurred in that particular way. Here, a constant feature of modern cosmology emerges. Each advance clarifies certain aspects, but exposes new limits. Even with inflation, when we trace the equations back toward the earliest moments, they lead to an extreme state where they cease to provide reliable answers. For many physicists, this limit indicates that a deeper theory is still missing, one that can describe the behavior of space and time under extreme conditions. Thus, while inflation brings coherence to the story of the early universe, the ultimate origin remains shrouded in mystery. The Big Bang may not have been an absolute beginning, but a transition. Before exploring those possibilities, a more basic question arises: what does it mean to speak of nothingness? Contemporary physics shows that even the vacuum is full of activity. In the quantum realm, the vacuum is a minimum energy state in which constant fluctuations arise. It is not a passive backdrop, but a field charged with potential. This idea transforms the notion of origin. If nothingness is not absolute, the birth of the universe could be the natural result of fundamental processes that are still poorly understood. However, this introduces a new paradox. If the vacuum possesses laws, it too requires explanation. Thus, cosmology advances by expanding our understanding, while continually pushing the boundary of mystery further away. The Big Bang ceases to be merely an initial point and becomes a permanent invitation to rethink what we mean by beginning, causality, and existence in a universe that defies our intuitions. For a long time, the singularity was accepted as an inevitable consequence of the Big Bang. When tracing the equations backward in time, the universe seemed always to lead to the same result: an extreme state in which density and temperature become incalculable. That limit marked the birth of space and time. Yet, the more closely this point was examined, the clearer a deep discomfort became. The singularity did not explain the origin of the universe. It merely signaled where our theories ceased to function. In physics, infinities are rarely interpreted as literal realities. They function as warnings. They indicate that a model has been pushed beyond its domain of validity. When an equation produces infinite values, it does not describe the ultimate nature of reality, but reveals the limitations of the theoretical framework being used. From this perspective, the singularity began to be seen not as a definitive answer, but as an unresolved problem. This discomfort led many scientists to question the idea of an absolute beginning. Perhaps the Big Bang was not the start of everything, but a transition. Perhaps the universe did not arise from nothing, but from a prior state that we do not yet understand. Under this view, the Big Bang ceases to be a final starting point and becomes a threshold between different phases of reality. One path explored to avoid the singularity was to rethink the nature of time. In everyday experience, time flows continuously, like an unbroken line. However, some theoretical approaches suggest that under extreme conditions, time might behave differently. Instead of flowing smoothly, it could advance in discrete steps, like a sequence of states. If time is not continuous, the notion of an absolute beginning loses force. The Big Bang could represent the passage from one physical state to another, not emergence from nothing. In this framework, the universe would not have been born, but would have changed phase. From this line of reasoning emerged cyclic universe models. According to these theories, the cosmos has neither a single beginning nor a definitive end. Instead, it undergoes cycles of expansion and contraction. A universe expands for billions of years, reaches a limit, and then begins to contract. That contraction leads to an extreme state that gives rise to a new expansion. In this scenario, what we call the Big Bang would simply be the rebound of a previous universe. Not a unique event, but part of a recurring process. Each cycle would inherit certain properties from the previous one, though transformed. Time, rather than having an absolute origin, would extend into the past and the future without a clearly defined starting point. The appeal of these models is evident. They eliminate the need for creation from nothing and offer a narrative in which the universe has always existed in some form, yet they also present profound challenges. One of the most important is the question of information. If each universe collapses before giving rise to the next, what happens to the information contained in its structure? Is it preserved, transformed, or lost? Moreover, current observations indicate that the expansion of the universe is not only continuing, but accelerating. This acceleration complicates the idea of a future global contraction. Cyclic models must explain how a universe undergoing accelerated expansion could reverse its behavior and begin to collapse again. Another approach to overcoming the singularity involves modifying our understanding of space at extreme scales. Instead of conceiving it as a continuous entity, some theories propose that space has a fundamental granular structure. At microscopic scales, space would be composed of discrete units, in much the same way that matter is made up of atoms. If space has a minimum structure, infinite compression is no longer possible. The singularity dissolves because there is a natural limit to how dense the universe can become. Within this framework, the Big Bang would not be a point of infinite density, but the moment when the universe reached its most compact state before expanding again. This conceptual shift also affects the notion of causality. In a universe where time may behave in a non-classical way, the relationship between cause and effect becomes more subtle. The Big Bang might not have a cause in the traditional sense, but instead be connected to prior conditions through laws that are still unknown. Here, an unsettling conclusion emerges. Perhaps insisting on the question, what happened before, reflects a limitation of our language and intuition. The beginning, as we imagine it, may not exist at all. Far from being a failure, this confrontation with the limits of knowledge is one of the greatest achievements of modern cosmology. Understanding the universe is not only about accumulating data, but about revising the concepts through which we interpret reality. Thus, in attempting to eliminate the singularity, science is not merely trying to solve a mathematical problem. It is seeking to redefine what it means to begin. The Big Bang ceases to be a primordial explosion and becomes a conceptual boundary, a point at which our ideas about time, space, and causality must be reconsidered. Perhaps the universe was not born. Perhaps it has always been in process. And perhaps the true challenge is not to discover what came before the Big Bang, but to learn how to think beyond the need for an absolute beginning. By abandoning the idea of an absolute beginning, cosmology was forced to reconsider an even deeper question. If the universe did not arise from a defined point, and if time itself may not have a clear origin, then what do we really mean by nothing? For centuries, nothingness was conceived as total absence, a void without properties. Modern physics has shown that this intuition is insufficient. Within the framework of quantum mechanics, the vacuum is not an inert space. It is a state of minimum energy in which constant fluctuations occur. Particles and antiparticles appear and disappear over extremely brief intervals. Although these processes are imperceptible on human scales, they are part of the fundamental fabric of reality. The quantum vacuum is not passive, but dynamic and active. This understanding transformed the notion of origin. If even nothingness contains activity, the birth of the universe does not require creation from an absolute void. It could be the natural result of quantum processes operating at a deep level. In this context, the Big Bang ceases to be the beginning of everything and becomes the start of a particular phase within a broader reality. However, this explanation introduces a new paradox. If the quantum vacuum possesses laws, structure, and properties, then it is not absolute nothingness. It remains something that requires explanation. Where do those laws come from? Why do those conditions exist rather than others? The mystery does not disappear. It is simply pushed to a deeper level. To address this problem, models emerged that expand the cosmic stage beyond a single universe. Thus arose the idea of the multiverse. According to this view, our universe would be one among many, each with its own physical laws and modes of evolution. In some models, the inflationary process did not occur only once, but continues to generate universes in different regions of space-time. Within this framework, the existence of our universe ceases to be exceptional. Some universes would collapse quickly. Others would not allow the formation of complex structures. Only a few would develop conditions compatible with life and with observers capable of reflecting on their origin. This idea is linked to the anthropic principle. We do not observe just any universe, but one compatible with our existence, because only in such a universe can observers arise. Another theoretical line suggests that our universe could be a kind of membrane embedded in a space of higher dimensions. Other membranes might coexist very close by, invisible to us. When these structures interact, the energy released could give rise to events equivalent to a Big Bang. In this scenario, the origin of the cosmos would not be unique, but the result of repeated processes. These ideas are difficult to verify. We have no direct access to other universes or to additional dimensions. However, they do not arise from fantasy, but from mathematically consistent models that seek to unify the known laws of physics. The challenge is not their internal coherence, but the lack of direct observational evidence. Here, cosmology faces a central dilemma. To what extent can a theory be considered scientific if it cannot be tested experimentally? At the limits of knowledge, physics moves along a blurred frontier between what can be demonstrated and what can only be inferred. Even so, exploring these hypotheses has profound value. It forces us to reconsider our most basic intuitions. Time may not be linear. Nothingness may not be empty. The universe may not be unique. Each of these possibilities challenges our understanding of reality. All of these theories share a common feature. They reject the idea of a simple, definitive beginning. The Big Bang ceases to be an isolated instant and becomes an episode within a much broader story. It may be the result of a fluctuation, a cycle, or a transition between deeper states. Perhaps we will never know with certainty which of these explanations is correct, But that uncertainty does not represent failure. It is a sign that science continues to move toward unknown territory. The true achievement of modern cosmology is not that it has closed the question of the universe's origin, but that it has transformed it. When we look at the night sky, we are not only observing stars and galaxies, we are observing the traces of a vast and complex process. Every atom in our bodies is part of that story. And even if we never find a final answer, the search itself reveals something essential. We are part of a cosmos that, even in its mystery, continues to invite us to think, to doubt, and to explore. Here, the answer does not end, but the question begins. The universe remains open, and understanding it may be less important than daring to explore it.